Welcome to the course Design of Reinforced Concrete Structures. In today's lecture, we are going to discuss regarding the topic neutral axis depth in limit state of collapse flexure. So, we will see how to find out the neutral axis depth as well as the moment of resistance in limit state of collapse flexure. So, limit state of collapse flexure. So, here we are going to calculate the neutral axis depth. So, first what we are going to do here is we are going to consider a singly reinforced beam section. So, here first let us draw a singly reinforced beam section. So, I am considering a singly reinforced beam and at some section A I have taken this. So, let the breadth of the beam be B and D be the overall depth of the beam. So, what is B? B here is the breadth of the beam. And what is D? D is the overall depth of the beam. Now what I have told here, we have considered a singly reinforced beam. So singly reinforced beam in the sense is a beam which is having reinforcement present only in the tensile zone. That is the so this is going to be a compression zone and this will be a tensile zone. So the reinforcement is present only in the tensile zone. So let us provide the reinforcement here. So these are the reinforcement AST. AST is the nothing but the area of steel reinforcement. Now, the distance from the topmost compression fiber to the center of the steel reinforcement is called as the effective depth D. Here D is what? D is the effective depth. And the distance from the bottom of the reinforcement to the bottommost fiber is called as the clear cover. Okay. So, this distance is called as the clear cover. So, if in any case, if effective depth is to be calculated, then how will calculate the effective depth? The effective depth D can be calculated by overall depth D minus the clear cover minus the diameter of the bar divided by 2 minus diameter of bar divided by 2. So why? So D is what the effective depth is? The distance from the topmost fiber to the center. So overall depth minus the clear cover minus the dia divided by 2 will give you the effective depth D. So D is overall depth minus clear cover minus diameter of the bar divided by 2. So now what here what we are finding out? We are finding out the neutral axis depth. So what is neutral axis depth? The neutral axis depth is here what we are going to find out the neutral axis depth. So first we will see what is a neutral axis. So the neutral axis is the axis at which the stresses are 0. So and this neutral axis will lie at the CG of the body. So this is going to be a neutral axis. Now what we have to calculate? We have to calculate the neutral axis depth. So neutral axis depth in the sense is what? The distance from the topmost compression fiber to the neutral axis is called as the neutral axis depth, and it is denoted by XU. So here what we are calculating in this limit state of collapse flexure, we are going to calculate the neutral axis depth XU. We are going to calculate what? The neutral axis depth XU, that is the distance from the topmost compression fiber to the neutral axis, which is XU. So for calculating the neutral axis depth, we are going to use the assumptions which are given in limit state of collapse flexure, because here I am considering a beam section. So based on the limit state of collapse flexure, so based on the assumptions of limit state of collapse flexure, we are going to find out the neutral axis depth for this particular singly reinforced beam section. So first let us draw the stress and the strain profiles for this particular singly reinforced sections based on the assumptions for limit state of collapse flexure. So if you remember the assumptions which you have learned previously. So what is the first assumption? The assumption is the plane sections remain plane before and after bending. So what does that mean? That means that the strain variation is linear. Okay. So first let us draw the strain profile. So from this what you can observe that the strain variation is linear. So that is from the first assumption what we have learned. And what is the next assumption? The next assumption is the maximum strain in the compression fiber is taken as 0.0035. So if you take this particular beam section, so what will be your compression fiber? This part is going to be under compression and this particular part is going to be under tension. So here what? The maximum strain in the compression fiber is how much it is? 0.0035. the maximum strain in the tensile reinforcement is 0.002 plus 0.87 Fy by Es. So where you will have the maximum strain? The maximum strain will be near the reinforcement, is it or not? Here you will have. So in the tensile reinforcement. So here what will be the maximum strain? The maximum strain. The maximum strain is 0.002 plus 0.87 Fy by. So here we are going to have our maximum strain. So this is going to be our strain profile. So this is going to be our strain profile. Strain. Now let us draw the stress profile. So what is the next assumption we have seen? The next assumption is up to a strain of 0.002. Up to a strain of 0.002. The stress strain curve for concrete is parabola, and from that the stress strain curve will be linear. Is it or not? So if we draw the stress profile or the stress block up to a strain of 0.002. For suppose here somewhere if the strain is 0.002, up to this what will be the stress strain curve? Up to that strain, the stress strain curve is parabola. So up to a strain of 0.002, stress strain curve is parabola in shape, and from a strain of 0.002, the stress strain curve is linear. That is, from here the shape is linear. So up to 0.002 it is parabolic, and from here it is linear. Okay. Now what is the stress in concrete? That is the design stress in concrete. We have already seen in the assumptions. It is 0.45 FCK. So in this particular part, what we are going to have the concrete. Here also we are going to have the concrete. But what in the assumptions only it is given that all the tensile forces are taken up by the steel reinforcement itself and none by the concrete. So the concrete is meant for taking all the compressive forces, and all the tensile forces are taken up by the steel reinforcement which is present here. So what you have in the upper portion of the stress block, we are going to have the compressive forces. That is, here we will have the compressive forces C, and at the tensile reinforcement, that is the steel, we are going to have the tensile forces. And what will be the stress here? Already it is given in the assumptions. So that is the design stress for steel is taken as 0.87 into Fy. So the design stress is taken here as 0.87 into Fy, and the design stress in the concrete is taken as 0.45 FCK. So here we are going to have the compressive forces, and here at the tensile steel we are going to have the tensile forces. So this is going to be our stress profile. So this is what? This is going to be our stress profile, and this is our stress block. Now what here? We have to calculate the neutral axis depth. That is, this depth is what we have to find out. XU. So calculate the neutral axis depth XU, first we have to find out the total forces of compression and the total forces of tension. That is, we have to calculate the forces, total forces of compression C and also the total forces of the tension T. First, let us calculate the total forces of the compression. So, the total forces of compression, it is, so the total forces of compression C is made up of two forces C1 and C2. That is, C is equal to C1 plus C2. So now we will see what is C1 and what is C2. So if you observe this particular stress profile, okay, so if you observe this particular stress block, up to a strain of 0.002, it is parabolic and here it is linear. Okay, that is the stress block is irregular in shape. So as the stress block is irregular in shape, we will divide this particular stress block into two parts. So let us draw separately this particular stress block. So up to a strain of 0.002, this is parabolic in shape and here it is linear. So this particular stress block, as it is irregular in shape, I have divided this into two parts. One part is a rectangular part and the forces in that rectangular part is taken as C1 and the other part is a parabolic part. And the forces in the parabolic part is taken as C2. So the total compression force C will be C1, that is the forces in the rectangular part, as well as C2, that is the forces in the parabolic part. Now let us find out the forces C1 and C2. So first let us find out the compressive force C1, that is for the rectangular part. So what is force? Force is stress into area. Stress is already known. So what is the design stress? It is 0.45 FCK into the area. The area for this particular rectangular part. So you have already known this is nothing but the breadth of the section which is taken here. And this distance is not known, that is the depth, that is the height of the section is not known. So first what we have to do, we have to calculate the individual heights of this particular rectangular portion as well as the height for this particular parabolic portion. Now we have already known the breadth, but the depth is not known yet. So first let us find out the depths for the rectangular portion as well as the parabolic portion. So for that what I am doing is, I am considering this particular strain profile. So let us draw the strain profile here. So what is the strain here? It is 0.002 and the maximum strain here is 0.003. This distance is how much? The distance is x. Now what I have to calculate? I have to calculate this distance. This distance will be similar to this and distance will be similar to this. So let the depth of the rectangular portion be x1 and let the depth of this portion be x2. Now what I have to calculate? I have to calculate the x1 and x2. So consider the similar triangles. So from similar triangles, how can you write down this? You can write this down as 0.0035 divided by xu is equal to 0.002 divided by x2. So from this you can get the value of xu as 4/7 xu. So from this you can get the value of x2 as 4/7 xu. Now calculate the x1. So how will calculate x1? xu can be written as x1 plus x2. So x1 will be xu minus x2. So x2 value is already known here. So from this xu minus 4/7 xu. From this we will get a value of x1 as 3/7 xu. Now we have found out the values of x2 and x1. So we have got the values here. So this is how much? It is x1 is 3/7 xu and this distance is 4/7 xu. Now find out the compressive force. This will be B. So C1 is what? It is the compressive force. Force is stress into area. So what is the stress here? It is 0.45 FCK into the area. Area for the rectangular block. It is B into D. D is 3/7 xu. So this is going to be a compressive force C1. That is stress into the area. That is 0.5 FCK into D into D. D here is 3/7 xu. Now let us calculate the compressive force C2 for the parabolic portion. Now let us calculate C2. So in the parabolic portion, so here also it is force is stress into area. So the stress is how much? It is 0.45 FCK into area. The area of parabola is 2/3 base B into height. The height here is 4/7 xu. Now what we have got? The compressive force C1 and the compressive force C2. So how can we find out the total compressive force? C is equal to C1 plus C2. So C is equal to 0.45 FCK B into 3/7 xu plus 0.45 FCK 2/3 B into 4/7 xu. So if you solve this particular equation, if you solve this, you will get the total compressive force C as 0.36 FCK B into xu. So if you will solve this, we are going to get the total compressive forces as 0.36 FCK B into xu. So these are the total compressive forces or the total forces of compression C. Now what? We have got the total compressive forces C as how much? 0.36 FCK B into xu. from the topmost compression fiber. That is, we have to calculate this particular distance. So a compressive force is acting in this particular area, but at what distance is it acting? So that is what we have to find out now. So let this distance be x bar. So what we have to find out here? We have to find out the x bar, the distance at which this compressive force C is acting. So for that, what we have to first let us draw the stress block separately. So previously, this is our force C1 in the rectangular portion and this is C2 in the parabolic portion. Now what? First we have to individually calculate the distances at what these compressive forces C1 and C2 are acting from the topmost compression fiber. So let this distance be A1, that is the distance of this compressive force C1 which is acting from the topmost compression fiber, and let the distance of the compressive force C2 acting from the, and let this distance of the compressive force C2 from the topmost compression fiber be A2. So first let us calculate the A1 and A2. So how we can calculate the A1 and A2? So the compressive force for this rectangular portion, it will act at the CG of this rectangular portion, and C2 will be acting at the CG of this parabolic portion. So we already calculated the distance x1 and x2. So what is x1 here? This distance is 3/7 xu. And this distance also we have calculated, which is 4/7 xu. So A1 will be what? The rectangle. For this rectangle, the CG. It is half into what is the distance here? It is x1, that is 3/7 xu, that is 3/14 xu. That is the compressive force C1 is acting at a distance of 3/14 xu from here. Now in the similar way, let us calculate A2. Okay. So what A2 will be? A2 will be x1 plus the distance at which this is acting, that is the CG of this parabolic part, that is 3/8 into 4/7 xu. So x1 is what? x1 is 3/7 xu. So here we can write down 3/7 xu. Now we have got A1 and A2. Now what we have to find out? We have to find out x bar. So how we can find out x bar? X bar can be calculated by force into the perpendicular distance C1 into A1 plus C2 into A2 divided by C1 plus C2 will give you the x bar value. So already we have calculated the value of C1, C2, A1 and A2. Substitute all the values here so that we will get the value of x bar as 0.42 xu. So So what does that mean? That means that the compressive force P is acting at a distance of 0.42 XU from the topmost compression fiber. So X bar here is what it is? 0.42 XU. So X bar here is what? There it is. That is the compressive force C is acting at a distance of 0.42 XU from the topmost compression. Now we have calculated the total forces of compression and the distance at which the compressive forces are acting from the topmost compression fiber. Now let us calculate the total tensile forces. So the total forces of tension T. Now we are going to calculate the total forces of tension. So here what? All the tensile forces, we have seen the assumption already. What is the assumption? That all the tensile forces are taken up by the steel. That is, the tensile forces are not taken up by the concrete. That is, the concrete tensile strength is ignored. So what? We have tensile forces at the present at the steel reinforcement itself. So T will be what? It will be stress into area. That is, what is the stress? That is the design stress. It is 0.87 Fy into area. Area of what? Area of the steel here. So how the area of the steel will be represented? It is represented by AST. So the total tensile forces is 0.87 Fy into AST. So now we have calculated the compressive force as well as the tensile force T. But from where this particular T is acting, at what distance is it acting? It is acting at a distance of D. D here is nothing but the effective depth. So the total tensile forces are acting at a distance of D. Here we have already mentioned it. Okay, from the topmost compression fiber. So now what? We have calculated the total forces of compression and also the total forces of tension. So for calculating the neutral axis step, the total forces of compression are equal to the total forces of tension. So that is taking into consideration the equilibrium. The total forces in the compression will be equal to the total forces of the tension. So the total forces of compression will be equal to the total forces of tension. So what are the total forces of compression? It is 0.36 FCK B into XU will be equal to 0.87 Fy into AST. So from this we can calculate the XU value. So what will be XU? XU is equal to 0.87 Fy into AST divided by 0.36 FCK into B. So this is the equation for calculating the neutral axis depth XU. So XU is 0.87 Fy into AST divided by 0.36 FCK into B. So this is how we will calculate the neutral axis depth XU. Now the two forces, that is the compressive force and the tensile forces, are developing a couple. If you see here, the compressive force and the tensile force is developing a couple. So from that what we can do is we can find out the moment of resistance. So the moment of resistance is equal to the moment of the couple developed between the compressive and the tensile forces. Now let us calculate the moment of resistance. So the moment of resistance denoted by mu. So let us calculate first the moment of resistance with respect to concrete, that is mu with respect to concrete. So what is moment? Moment is the force into the perpendicular distance. So with respect to concrete, what we'll have? We'll have the compressive force into the perpendicular distance. So first let us find out the perpendicular distance between the two forces. So for that, let me draw the stress block here separately. So here we have the tensile force T, here we have the compressive force C. So this is going to be a perpendicular distance. So how we'll calculate the perpendicular distance? So what is the distance from the topmost compression fiber to the tensile reinforcement? It is D. Okay, D minus this distance. What is this distance we have calculated? 0.42 XU. So D minus 0.42 XU is the distance between the compressive force and the tensile force. So that particular distance, perpendicular distance, is called as the lever arm. Okay, so it is lever arm and it is denoted by Z. So Z is equal to D minus 0.42 XU. Now what? Let us calculate the moment of resistance with respect to concrete. That is the compressive force. What is the compressive force? We have already calculated. It is 0.36 FCK B into XU into the perpendicular distance. Here it is nothing but the lever arm Z. It will be D minus 0.42 XU. So this is the moment of resistance with respect to concrete. In the similar way, we can calculate the moment of resistance with respect to steel. So the moment of resistance mu with respect to steel reinforcement. It will be what? It is also the force into the perpendicular distance. So here it is T. So what is the force? It is 0.87 Fy into AST into the lever arm. It is D minus 0.42. So this is the equation for finding out the moment of resistance with respect to steel. That is 0.87 Fy into AST into D minus 0.42 XU. So these are the basic equations, and from these equations you can derive the other equations also. So these are the basic equations for moment of resistance with respect to concrete and steel.